In Unit 3, we looked at congruent figures, and we looked more specifically at congruent triangles and proving congruent triangles. So, two key ideas when we're talking about proving congruent triangles. The first key idea is when two figures are congruent if and only if there exists a sequence of rigid motions that will map one figure onto the other. So, what this means is we can prove that two figures have to be congruent to each other if we can start with one figure and perform a translation, rotation, or a reflection or a combination of those things to get to the other figure. Basically, it means that all of the angles would map onto the others and all of the sides would map onto the others, keeping the length and the angle measures the same. So it would produce congruent figures. The second key idea is that we could use any of the 5 congruence theorems to prove two congruent triangles. So these 5 congruence theorems are really like shortcuts. So instead of having to show all sides and all angles are congruent in order for the triangles to be congruent, we have 5 different shortcuts. So we only have to show 3 things instead of all 6 things being congruent. So the first one we looked at was side, 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 which means that in these two triangles, if I could prove that the 3 pairs of corresponding sides are congruent, that would guarantee that everything else has to be congruent. So it would guarantee that the angles are congruent as well, which would force the two triangles to be congruent. Another theorem we looked at was side angle side. So if I can prove 2 sets of sides that correspond are congruent and the angle between them are congruent, then I can say the triangles are congruent. Notice that the A is between side, angle, side, so it has to be the angle that touches the 2 congruent sides. Then we had angle, side, angle, so that means, again, the side, or the S, is between the 2 A's. So that means if I have these 2 sets of congruent angles, I'm looking at the side that's touching both of those angles, so the side included in those 2 angles. Then we had angle, angle, side, or side, angle, angle. So in this case, I have my 2 sets of angles just like the last one, but the side has to be outside of the 2 angles. So it's only going to be touching one angle, not both of them. So it could be this side here that I have drawn in, or it could be this set of sides over here. And then the last one is HL, and I call this HL-right triangle because the only time that you can use HL is whenever you have right triangles. So you still have 3 pieces of information to prove, the H, the L, and the right triangle part. So the H stands for the hypotenuse, so you have to have the set of hypotenuses from each triangle being congruent. And then you have to have one of the legs. So the leg, you can pick this leg down here to be congruent, or I could prove this leg on this side congruent. And the 2 theorems, or the 2 shortcuts that we found that do not prove congruent figures, are AAA, or angle, angle, angle. So if we have 3 sets of corresponding angles that are congruent, this does not prove congruent triangles. They may be congruent, but it does not force them to be congruent. They could be different sizes. They could actually be what we call similar figures. One could be bigger than the other. They have the same shape, but the sizes are going to be different. And then the other one is whenever you have side-side angle, this would actually produce 2 different types of triangles. So this is when your angle is not between the 2 sides. So see how the angle is only touching one side? It's not touching both of the congruent sides. Where side, angle, side, the angle is touching both sets of congruent sides. The only case of side-side angle that works is whenever you have right triangles. So if you notice, this is really a side-side angle case, but because it's a right triangle, it forces the scenario to only ever create one set of triangles as long as you're given the side-side angle. So that would produce congruent figures. So just keep in mind, if you ever see side-side angle, look for a right triangle, because if it's a right triangle, you can use HL. If it's not a right triangle, then you can't prove the 2 figures are congruent. On the next page, I'm going to just let you kind of read through these. These are just all different reasons that you can use in proofs. There's some really common ones using line segments. We have midpoint, bisector, perpendicular lines form right angles, vertical angles when we talk about reasons that use angles. We have an angle bisector makes 2 congruent angles. So these are all different things that you want to make sure that you know and you're prepared to use them in a proof. One thing I want to point out, though, is always remember to mark your diagram. Whenever you're given a proof, always mark the diagram so that you can see what you're working with. Um, Also, another thing to look at here is the parallel lines. So parallel lines being cut by a transversal. If you ever have a scenario like that, you're looking for those alternate interior angles that are congruent or alternate exterior angles. So you're looking for these different types of angles. Alternate interior angles come up quite a bit. That's when you have like the Z shape. And then we already talked about these methods here. In the diagram, if you ever had shared sides or overlapping triangles, look for the reflexive property. Look for supplementary angles when you have two angles that form a line. Look for vertical angles. Remember, vertical angles, you have the X. Look for isosceles triangles, because if you have two congruent base angles, then you have two congruent sides. If you're ever trying to prove a set of sides or a set of angles, then you're going to be using CPCTC. Make sure that if you don't remember the acronym, that you just explain it. Corresponding parts of congruent triangles are congruent, or if you have two triangles that are congruent, then their parts must be congruent, something along those lines. And then let's look at just some examples. So this first example here, I'm given segment AB and DC are congruent. I'm given AC and DB are congruent, and I want to prove the two triangles are congruent. So I want to prove triangle ABC is congruent to triangle BDC. So I'm going to go ahead and I'm going to set up the two columns. And we have our statements on one side and our reasons on the other. And remember, we always start with the given. So AB is congruent to DC. We have AC is congruent to DB. So these things are given. And then we need to be able to prove that these two triangles are congruent. So looking at the picture now, because I can't really make any further conclusions with these two givens, but looking at the diagram, I see a shared side. I see the reflexive property. So I can now add in my proof, BC is congruent to itself by the reflexive property. And now I have enough information to prove what I'm trying to prove, that the two triangles are congruent by side, side, side. So side, side, side. So that's it. So that one's a fairly basic proof. Let's look at this next one here. So I have AC is congruent to DC, and BC is congruent to CE. And I want to, again, prove these two triangles are congruent. So I want to prove this triangle is congruent to this triangle. So to do this, again, set up your two columns. Statements, reasons, and write your givens. So based on my givens alone, I can't really make any further conclusions. So whenever you've used up your givens and there's no further conclusions you can make, this is where you want to go in the diagram and start looking for what kind of conclusion can you make from the diagram. And when I look at the diagram, I saw the X right away, so I saw vertical angles. So I'm going to call those vertical angles 1 and 2, and then I can state that they're congruent. So angle 1 is congruent to angle 2, because vertical angles are congruent. And then that's going to be enough information to say that the two triangles are congruent. By side, angle, side. And then the last proof here, notice this time I'm not trying to prove triangles are congruent. I'm trying to prove two segments are congruent. So as soon as I see this, I'm thinking to myself, I have to use CPCTC. I have to show that the triangles are congruent so that I can say their corresponding parts are congruent. So the first thing I need to do is prove that my two triangles are congruent. So the triangles that these segments belong to. So EJ and HJ are the two segments that I'm trying to prove. So that means HJ belongs to this triangle, this red triangle, and EJ belongs to this purple triangle. So those are the two triangles that I need to prove are congruent. So I have to first prove that triangle FEJ is congruent to triangle GHJ. So let's go ahead and set that proof up. So we have two columns again. You can go ahead and write your givens in there and mark your givens. So we have parallel lines this time. So again, remember, whenever we see parallel lines, this is kind of like a red flag that we should be looking for maybe some alternate interior angles that are congruent corresponding, alternate exterior angles. A lot of times you're going to see those alternate interior angles coming up. So when I go back to the diagram and I mark, I have EF is congruent to HG. So that's a set of sides. And I also know that EF is parallel to GH. So we mark parallel lines using the arrows. And right away, as soon as I mark parallel and I see this picture, I'm seeing that Z shape. I'm seeing those alternate interior angles here. Think about it as here's my transversal, here, or here's my two parallel lines, here's my transversal, and I have two angles that are in the inside of the parallel lines on opposite sides of the transversal, so those two angles have to be congruent. So I'm going to call it angle 1 and angle 2. So I can say angle 1 is congruent to angle 2 because parallel lines imply congruent alternate interior angles. Now, for the next set of angles that you can prove vertical angles again, or you could prove these as alternate interior angles. So see how I have another Z shape? So these angles here are also congruent because those are also alternate interior. They're on the opposite sides of the transversal in the interior. So it's up to you which set you want to use. If you use the alternate interior angles, you'll be proving the triangles are congruent by angle, side, angle. If you use the vertical angles, then you'll be using angle, angle, side. So I'm going to go ahead and I'm going to use these alternate interior angles. So I'm going to call them 3 and 4. So these 3 and 4 represent the angles here. And the nice thing about doing that is now I don't have to write another reason because angles 3 and 4 are congruent for the same reason as statement 3, statement and reason number 3. So I just grouped it with it. So now I can say that the two triangles are congruent by angle, side, angle. So triangle FEJ is congruent to triangle GHJ by angle, side, angle, which now allows me to prove those corresponding sides are congruent. So EG or EJ is congruent to HJ by CPCTC. So as long as the triangles are congruent, the corresponding parts have to be congruent as well.